Given, an n×n matrix where each row and each column is sorted in non-decreasing order, plus an integer k, return the kth smallest element among all n² entries. Example 1, a 3 by 3 sorted matrix with k equal to 8. Count values in sorted order. The 8th position lands on 13, so output 13. Rows increase left to right, and columns increase top to bottom. So the minimum sits at top left and the maximum sits at bottom right. The answer value must be between 1 and 15. So we binary search this value range, not matrix indices. Now watch one staircase count with a sample guess x equals 11, step by step. 11 is just a demo guess near the middle. Start at bottom left, 12 is greater than 11, so move up. At 10, 10 is less than or equal to 11. Because the column is sorted upward, every cell from row 0 down to this row is also less than or equal to 11. That is our +1 cells, so add 2, then move right 1 column. At 11, still less than or equal to 11. Again count the whole column prefix from row 0 through this row, our +1 equals 2, add 2, then move right 1 column. At 13, too large, so move up. At 9, 9 is less than or equal to 11. The column prefix through this row is just row 0, so our +1 equals 1, add 1, move right, and we exit the grid. Now binary search on values. If count is less than k, move right to larger guesses. If count is at least k, keep this guess and move left. The answer is the smallest value whose count reaches k. Solution idea: binary search on values, not indices. Set low to the smallest matrix value and high to the largest value. The kth smallest answer must lie in that inclusive range. Each iteration sets mid to low plus half of high minus low using integer division. That avoids forming low plus high first, which can overflow in fixed width integers and is the usual safe midpoint. Mid does not need to appear in the matrix, we only use it as a threshold to count how many entries are less than or equal to mid. Demo threshold mid equals 8. Start at bottom left. 12 is greater than 8, so move up 1 row in the same column. At 10, 10 is greater than 8, so move up 1 more row in the same column. At 1, 1 is less than or equal to 8. In this column, only row 0 qualifies at this position, so add row +1 equals 1, then move right 1 column. At 5, 5 is less than or equal to 8. Again only row 0 qualifies here, so add 1, then move right 1 column. At 9, 9 is greater than 8, so move up until we exit. The total count of entries less than or equal to 8 is 2. First binary search probe, mid equals 8. Count entries less than or equal to 8 is 2, which is below k equals 8, so 8 is too small. Increase low to mid +1, so low becomes 9. Second probe, with low 9 and high 15, mid becomes 12. Count entries less than or equal to 12 is 6, still below 8, so increase low to 13. Third probe, with low 13 and high 15, mid becomes 14. Count entries less than or equal to 14 is 8, which reaches k, so 14 is feasible. Shrink high to mid, so high becomes 14. Fourth probe, with low 13 and high 14, mid becomes 13. Count entries less than or equal to 13 is 8, still feasible, so shrink high to 13. Now low equals high equals 13, so the search stops. 13 is the smallest value whose count reaches 8, matching the kth smallest matrix entry. Let n be the side length of the n by n matrix, and d the gap between the largest and smallest matrix values. Time is O of n log d in the worst case, each binary search probe runs one bottom-left staircase walk that takes at most order n steps, and we need logarithmic nd probes over the numeric range. Auxiliary space is O1 beyond the input grid, only a few indices and counters. Function kth smallest takes the sorted matrix and k. Read the minimum value at the top left corner. Read the maximum value at the bottom right corner. Binary search while low is still strictly less than high. Pick mid as low plus half of high minus low using integer division, instead of low plus high then halved, so the sum never blows up in bounded integer types. Count entries less than or equal to mid with the staircase helper. If that count is smaller than k, the kth smallest must be larger than mid. So raise low to mid plus 1. Otherwise we already have at least k entries at or below mid. Shrink high down to mid because the answer could still be mid or smaller. When the two bounds meet, return that value. Helper counts how many entries are at most the threshold x. Let n be the row count, rows and columns are both length n. Start at bottom left with row index n-1, column 0, and 0 count. Walk while the row index is non-negative and the column stays inside the grid. If the current cell is at most x, add every cell above it in this column, then move right. Else this cell is too large for the threshold at this row. Move up one row in the same column. Return the accumulated count.